Today, I want to talk about hooking this Richardson's extrapolation idea together with this mathematical induction idea that we talked about previously, which will allow us to figure out something. Remember the premise. We have some quantity r that we're interested in calculating, and we have some approximation method that uses a spacing, which we call h. A of h is the approximation based on spacing h. This is going to be what we're wanting plus some error term. We will assume that we can write the error as a power series. It's the sum j equal 1 to infinity, alpha number j times h raised to the j power. Using this idea, we worked out a way to eliminate the h to the first power in the error term and the h squared as well. We figured out that if you calculate a table of numbers with indexes I and j, ti0 being the approximation based on h over 2 to the I power, and then taking combinations of previous columns in this method, we figured out that column k equal 1 has no h to the first power term in its error formula for the approximations involved. We proved that the k equal 2 column has no h squared term in its error expansion. We conjecture that that pattern will continue, and that's what I want to talk about today. For the rest of my discussion today, I'm going to call this the Richardson's algorithm so that I don't have to keep writing all this stuff over and over again. When we talked about induction, we looked at some special cases of that sum that we were talking about. We convinced ourselves that the statement was true if you only had one term or two terms or three terms, and then we did the induction argument to show that it's true in general. What I'd like to do now is the same thing, except I want to look at the numbers that are in the Richardson's table instead of those sums like 1 plus 2 plus 3 plus 4. I want to look and see what the error term is going to look like in these approximations that are in column k equals 0. Ti0 is going to be the actual result plus the sum j equal 1 to infinity alpha j times the jth power of whatever the spacing that I'm using to get ti0 from. And because of what we just said about the Richardson's algorithm, I can write that down. Which, writing a little bit of algebra, I can write as r plus the sum j equal 1 to infinity of 1 divided by 2 raised to the I times j power times alpha j times h to the j power. Now, I've done these calculations right before I started doing this video, so I'll tell you ahead of time something that's going to happen. When I look at later columns in the t table, in this sum, this factor, that factor, and h to the j will always be there. In view of what I'm about to do, it's convenient to make a comment. If I look at 1 divided by 2 raised to the power, number I minus 1 multiplied by j, I can write it that way, I can write it that way, and 1 over 2 to the negative j power is 2 raised to the j power. So anytime I have an expression that looks like that, I'm going to feel free to just write it this way. According to the Richardson's algorithm, the way that I'm going to get the numbers in column k equal 1 of my table is t, row I, column 1, is going to be 2 raised to the 1 power times ti0 minus the number in the column k equals 0 that is immediately above ti0, ti minus 1 comma 0, divided by 2 raised to the 1 power minus 1. It may seem silly to leave this written as 2 to the first power minus 1, but it will be informative shortly. I have a literal formula that tells me what ti0 is. It's just this formula, which simplified down into this formula. When I subtract away this part on the numerator, I'm going to have something in column 0, so it will be described by a formula like this, except the first index is not I anymore, it's I minus 1. So I'll be subtracting away r plus the sum j equal 1 to infinity, alpha j h to the j divided by, it's not 2 raised to the I times j power, it's 2 raised to the number I minus 1 multiplied by j power. This is why I wanted this comment. That's the same thing as 2 to the j power divided by 2 to the I times j power. This is beginning to look pretty bad, but what I'll do is I'll take this term and group it with that one, and then I'll group the two infinite series together, and then I'll have to remember to divide both things by 2 raised to the 1 power minus 1. If you'll observe, in the infinite series that remains, each term is going to have alpha j, each term is going to have h to the j, each term is going to have 2 raised to the I times j in the denominator of a fraction, so actually I can simplify this a good deal. For the numbers that are in column k equal 1, we now have a formula for ti1. It's the actual thing we're interested in, plus this infinite series. This is actually very interesting to me because there's going to be different terms to add together. The j can be anything from 1, 2, 3, and up, but in particular, if you look at the h to the 1 power term, the j equals 1 term, you'll have 1 over 2 to the I times 1, you'll have some unknown coefficient, you'll have h to the first power. This fraction will have something that's not 0 on the bottom, and when j is 1, the top is going to be 2 to the 1 minus 2 to the 1, which is 0. This shows me, if I didn't believe it already, that the numbers in column k equal 1 of my Richardson's table have no h to the first power term in their error expansion. When j is 1, this term is 0. If I want to look at column k equal 2 of my table, I'll use this formula, which is how we said we were going to calculate those Richardson numbers. This is going to be fairly messy, but it's just going to be a bunch of algebra. After we do this one, the pattern will suggest itself. We'll make a guess or conjecture, and then we'll use mathematical induction to prove that that guess is correct. Using our Richardson formula, ti2 is 2 raised to the 2 power times ti1, which we previously had gotten a formula for, minus t number I minus 1, comma 1. That only changes that, and we've already stated that if I take I minus 1, multiply it by j, and raise 2 to the resulting power, what I get is 2 to the j over 2 to the ij, alpha j, h to the j power. Two squared times r minus r. I'll write that out separately. Then I have two infinite series, each one of which is going to have a 1 over 2 to the ij, alpha j, h to the j in it, among other things. In this one, in this first series, I'll have an additional factor of 2 squared, so I'll write that there. In this new sum, there are certain things that are in common and a few things that are not. There's a 2 to the 1 minus 2 to the j in both pieces. There's a 2 to the 1 minus 1 in the denominator in both pieces. There's a 2 to the I times j. There is alpha j and h to the j. As we did before, I'll collect the terms that have r in it over 2 squared minus 1 and write that separately. And then inside the brackets, if I factor out everything that I can factor out, all that's left is going to be 2 squared minus 2 to the j power. Before we proceed, let's state the results that we just got. The initial approximations were in column k equals 0. The numbers that were in column k equal 1, ti1, are the actual thing we would like to know plus a sum. This sum has factors in it. There's a 1 over 2 to the ij power, there's alpha sub j, h to the j, and in addition, there's this fraction 2 to the 1 minus 2 to the j divided by 2 to the 1 minus 1. After calculating ti2, what we found out is it's the same formula except for one thing. The r is the same. 1 over 2 to the ij is the same. Alpha j is the same. H to the j. There's a 2 to the 1 minus 2 to the j in both of them. 2 to the 1 minus 1 on the bottom of the fraction. The only thing that's new is we have a factor of 2 squared minus 2 to the j upstairs, and one of 2 squared minus 1 downstairs. The first observation I'd like to make is this. If j is 1, then this factor will be 0. There will be no h to the first power term in the error. But even better, when j is 2, this factor will be 0. These numbers will not have an h to the first power term in them, nor will they have an h squared term. But even better than that, look at this formula, look at that formula, look at that one again, and I've got a guess, I've got a conjecture. I'm going to guess that TIK is the actual thing we're interested in plus a sum. The terms of this sum are all going to have a factor of 1 over 2 to the ij, a factor of alpha j, an h to the j, and there's going to be a fraction. When we went from the first column to the second column, we introduced an extra factor. So I predict, I guess, I conjecture that every time I go to the next column, I'm going to pick up an extra factor upstairs and an extra factor downstairs. So I would have 2 to the k minus 2 to the j, 2 to the k minus 1 minus 2 to the j, and just keep doing that until I get down to 2 to the 1 minus 2 to the j. These are the constant factors that correspond to the ones upstairs. Constants with respect to j, that is. I am guessing that this is right. I know it's true if k is equal to 1. I know it's true if k is equal to 2. In an exactly analogous way, I'm going to use mathematical induction to show that this is true for all columns in my table. Similar to what we did before, I'm going to have a hypothesis, hk. hk is the thought that the entry in the Richardson table is this formula that I'm guessing. We already know that h1 and h2 are true. If h of a certain index is true, is enough to guarantee me that h of the next index is true, I'll stand up, square my shoulders, and say, by the principle of mathematical induction, hypothesis hk is true for all relevant values of k. It's important to understand that I shouldn't get hung up on the exact name of indexes. If I assume that this hypothesis is true for a given column index, and then I can show that it's true for the next one, it doesn't matter what I call those indexes. The way I have my formulas written here, it'll be more convenient for me to think about what happens when I calculate t number ik in terms of numbers from the preceding column, the one where the second index is k minus 1. So let's suppose that hypothesis k minus 1 is true. What that means is that t I comma k minus 1 can be calculated using this conjectural formula that we just had. Using the Richardson's algorithm, tik will be computed in this manner. Ti comma k minus 1 will be given by this formula. I must multiply that by 2 to the k power and then subtract away ti minus 1 k minus 1, which I will write down using this formula, except wherever I see I'll write down I minus 1 instead. The only place that I see that I, though, is right there, and we've already decided what's going to happen when I change the I to I minus 1 in that. As stated, I write down what ti k minus 1 is based on the induction hypothesis. When I replace the I with I minus 1, as we previously seen, this factor turns into 2 to the j divided by 2 to the ij. So I'll take this, multiply it by 2 to the k power, subtract that, and then divide the entire result by 2 to the k power minus 1. This is rather ugly looking, but will simplify nicely. I am going to cheat a little bit here. What's going to happen with these r's? In the numerator of the fraction that has that as its denominator, I'm going to have 2 to the k power times r. Later I'll subtract r. That's 2 to the k power minus 1 times r divided by 2 to the k power minus 1. This contribution with that contribution in the end is just going to give me an r. The rest of it I have to be a little bit more careful about. When I combine these two series, I'm going to compare different things that are in different terms. In the h to the j power term, in both of them, there will naturally be an h to the j power. There will be an alpha sub j. This fraction and this fraction show up as factors. I can factor everything out except 2 to the k and 2 to the j, and I'm doing subtraction here. What I'm going to do is to take this new factor and write it in the numerator of the fraction out front. Also, I'm going to bring this factor, which doesn't depend on j any at all, inside and write it in the denominator out front. If hypothesis k minus 1 is true, then this formula is true. However, this formula being true is what we mean by h number k. Having already established that h1 and h2 are true, this fact tells me that I can stand up, square my shoulders, and say, by the principle of mathematical induction, every number in my table is described by this formula. This is an established fact now. After all of this work, you kind of think of the old cartoon character Marvin the Martian, who would say,
isn't that lovely?
When in fact it wasn't lovely at all. It was going to be some earth-shattering boom. This, though, really is lovely. This is good news. Imagine that I start calculating these t numbers, and I've just gotten done calculating column number k. In this sum, j takes on various values. If j is 1, then that factor is 0, and the coefficient of the h to the 1 term is 0. If k is 2, the next factor over will be 2 squared minus 2 to the j. 2 squared minus 2 squared. The numerator will be 0. The coefficient of the h squared term will be 0 also, and so on and so forth, all the way out to the alpha k h to the k power term. There's going to be some numbers and a factor of 2 to the k minus 2 to the k, which is 0. This proves to me what we thought was true is true. The error term for tik has no h to the first, no h squared, no h cubed, all the way out to no h to the k power term. If I look at one of these tiks, the power series that represents the error, how different tik is from the actual value r, starts off with h to the k plus 1 power. This is what we thought was going on, but now we're not guessing anymore. We know this to be true for a fact. Things are acting the way we figured they were acting. In the numerical analysis class that I teach, usually I don't go into this much detail for two reasons. One, people tend to not like proof things like this very much, and number two, it chews up a rather large amount of time. That's why I decided that it'd be good to do it in one of my rambling summer videos, which turned into 4 or 5 rambling summer videos. Hopefully, though, everybody can see what's clearly going on here. I'm not sure what my next rambling video will be, but in the meantime, I hope you're having a good day, and I'll talk to you again soon.